Okay, I think we have a quorum, so we'll get started. I should warn you, this is probably going to go clear till the end, so may not have time for questions, but if you can save them till the end, I'll try to get to them. If we completely go over, you can always email me, so I'll share my email address at the end. So my name is David Borel. I'm a manager in engineering on our SDK team at Oculus. I've been here about 3.5 years, and we've been working on a variety of things in engines to support easy VR development and high performance. And this is kind of the way that like 90+% of our developers reach the SDK. So Unity has been a pretty dominant interface for that ever since we began. So it's always been in our interest to have a really good developer experience in Unity, and that's kind of what my team focuses on. So today I'll be talking to you about kind of what our SDKs do on both PC and mobile. I'll kind of be exploring them in parallel so you can compare them and understand the relative performance and functionality trade-offs. And then we'll spend most of the time understanding the performance envelopes that you have available and the quality impact and the kind of quality performance trade-offs you can make. And there are some perceptual issues that come into play here, and we'll talk briefly about those, but there's some other talks that go into more depth on the human-computer interaction aspects of it. This will be mainly about performance analysis and debugging. So we'll kind of approach it this way. I'll do a quick 0 to 60, and then talk a little bit about the perceptual psychology that motivates some of the quality and performance issues we'll talk about later. Then I'll relate Gear VR and Rift rendering, but some of the concepts do apply to Vive and PSVR and Google VR, so most of this should be useful regardless of what headset you're targeting. And then I'll talk through some tools that you may not know about and wrap it up with the Q&A if we have time. Okay, so if you want to enable VR in a project in Unity, fortunately it's really easy. Unity's done a great job of exposing this. There's just a checkbox in player settings. And now as of Unity 5.4, there's a list of supported devices that you can prioritize. So you can have it try the Rift first and then fail back to Vive or whatever. You know, I'll switch that if you want, if you're from another company. But it's really easy, and on PC by default, the list is Rift and then Vive because the Steam VR SDK also supports the Rift. So it'll by default use LibOVR to target the Rift if attached, and use Steam VR to target the Vive, so that you get kind of the most favored path to each headset. If you just hit play in the editor, even if you're using Gear VR, if you have a Rift attached, it will render to the Rift in preview mode, so you can rapidly iterate. So I do recommend, picking up a Rift. I'm going to try to eke as much money out of you as possible as an Oculus employee. But it really does speed up the workflow. Also, Unity's been adding some features to make it possible to rapidly iterate without a Rift. There's the new code-only deployment option, so you can copy only the managed assemblies over to the device on each iteration, which can cut like several minutes out of your cycle. And there's also future work and development to make it even better. So what do our SDKs do fundamentally? When you hit play, normally it just renders directly to the graphics back buffer, or depending on how your stack is set up, it may be a texture and then a compositor. But the point is, with VR, those buffers get a lot more post-processing. So our SDK takes the rendered images, and there are two, one for each eye. That's how we create stereo disparity, is by showing different images to your eyes. And unfortunately, we can't control like the focal distance and other things about the image. We can only show you what we call disparate images that cause divergence, and those are the cues your brain uses to infer depth in the content. So we fundamentally have like a cell phone panel, basically. It's a little bit different now, but we basically have magnifying glasses in front of a cell phone panel, and our post-processed images show up on that panel at 90 frames per second. And we continue displaying those frames at 90 hertz, even if you aren't synthesizing them that fast, and I'll get into that later. But the most obvious thing that our SDK does, who here has worked with DK1? Anybody? All right, hardcore. So yeah, like 3.5 years ago, we had a developer kit that had an open source SDK, and you can go in there. It's, the source is still floating around the internet. You can go and see how that worked. But we had a per pixel raycast that was perturbing the ray direction based on the lens distortion. So we're counteracting a pincushion distortion caused by the lens with a barrel distortion. And once you get both of those effects applied, then you get back to a rectilinear image applied to your eye. But the main difference is that the pixel density has been kind of changed across the face of the image, kind of minifying the edge of the image and magnifying the interior of the image. So we're working on kind of advanced ways of cutting the shading rate around the periphery with a couple of different approaches. Nothing we can announce just yet, but you've probably read, who's seen the papers from NVIDIA about lens match shading? There's some really cool techniques that people have been exploring. So lots to come there, but there's unfortunately a lot of work being done for the periphery, which is the least salient. So there's a lot of opportunities to optimize VR rendering. Anyway, that's what our distortion rendering does. In addition, and I'll talk about this more later, we perform like latency correction and a couple of other image corrections. And our SDK also performs head tracking. So if you're wearing a Gear VR, there's an inertial measurement unit, which is a gyroscope and accelerometer inside. So I've shown a picture of the Innovator Edition headset there with the front ripped off, and you can see that black chip there. Those are commonly called, I think the common chip is a 9-axis, but they provide a really noisy position and rotation reading at about a kilohertz. And that's about the data rate we need for VR, but unfortunately we can't deal with the noise. So we can't actually give you the position reading we get from that. It drifts just far too quickly. If you try to use the position reading from one of these IMUs, you'll quickly see, you know, the head pose go flying away from the origin, and it's not useful. We've tried a variety of things to keep that kind of centered. It's not easy. Fortunately, it is a lot easier for the rotation, which also has noise. We're able to detect the gravity vector. There's always 9.8 meters per second squared pointing in some direction, so we figure out, you know, kind of down must be that way. And we can keep the horizon flat. And then we've done some filtering to figure out the correct yaw without using a magnetometer. So we didn't have to charge more for the headset. On the Rift, in addition to that IMU, we have low-frequency positional tracking, and actually there's an orientation reading coming in as well from computer vision. So if anyone, who's familiar with the ransack algorithm? Okay, one person, all right. Awesome. That is like, some people sarcastically say that's like one of the only reliable computer vision algorithms. Anyway, the point is, our computer vision system looks at LEDs, infrared LEDs on the Rift. They're actually embedded underneath the cloth of the Rift, which is just stretched. The fiber is not actually transparent, but it's stretched far enough that the light shines through. And, our computer vision, our infrared camera can detect the orientation and position of the constellation of LEDs based on the way they project onto the camera image. So we do that at about 30 hertz. So that's not fast enough for VR. We have to fuse that data with the high-frequency IMU data to get an aggregate reading. So we have different ways we do that in different situations. But you can think of it like low-pass and high-pass filtering in audio or other frequency domain issues. I should also mention that with the launch of Touch, we added support for multiple computer vision tracking cameras. So you can have up to 3 of them now. Actually, 4 should be possible in the near future. Hope that doesn't lead to a press release. Anyway, yeah, that does work pretty well. Also, we enabled USB 2, so you can have like really long runs of cable. I actually use USB 2 for most of my sensors. When we initially launched Touch, that was not very efficient, but we've optimized it significantly, and now I have like 50-foot runs of USB 2 cable in my house, and it works pretty well. That was one of the limitations on the usable size of tracking space. And I should also mention that on Gear VR, and also if you're using Rift and can't get a valid position reading, we fake the position of your head. So we assume that your head is orbiting around the base of your neck. I forget which vertebrae it is, but basically the ball on a stick model where the point between your eyes is kind of just orbiting at a fixed radius. And that's why when you rotate your head on Gear VR, the world does not seem to translate, or at least only very slightly. And that does not apply if you're doing 360 video. In 360 video, typically, there's not a different parallax for each viewing angle, so it will appear that your head is kind of rotating around the center point between your eyes when you rotate your head. Hopefully one day we'll get past that artifact. I encourage you to go check out the Facebook 360 booth. We've got some camera technologies that may help there. Okay, so with all this tracking and distortion rendering going on, the app still has to render. And so the way we typically work is give you a pose at the beginning of a frame, and then you render your textures, the eye buffers, and Unity abstracts those in a similar way to how it does the back buffer normally. So unfortunately, you can't really like read back from them easily. You can actually use like read pixels and whatnot, but that will sometimes have different numerical conventions. It'll be flipped and stuff. We made screenshot work and stuff like that. But there's, for example, masking occurring to prevent over-rendering with symmetric frustra that we're rendering. Anyway, this is kind of more in-depth than I meant to go. The point is that these eye buffers are abstracted and passed off to us every frame. And it takes Unity typically like 11 or more milliseconds to render. Well, hopefully not more. Up to 11 milliseconds to render each frame. And so the position and rotation data that it got at the beginning of the frame is no longer valid by the time we get the image data back. So that's why we need to perform an additional latency correction at the end of the frame. We do manage the frame timing, so we know roughly when scanout is going to occur at the time Unity hands us those eye buffers. And we can also predict, based on kind of running averages, how long the frame's probably going to take to render. So we try to kick rendering off at the right time, such that we balance latency and throughput. And we also try to leave as little slack at the end of the frame as possible. So dynamic prediction is kind of a set of techniques we use in our SDK to keep track of how far out the scan out is from right now, and help Unity maximize quality and performance. So the moral of the story is you don't have to worry about that. We take care of that for you, and it's all kind of baked into the time at which your code starts running. So how do we implement our distortion rendering? In the DK1 days, as I mentioned, we had per pixel ray that we were casting based on lens distortion. It was like slightly more accurate. But what we do now is vertex-based distortion, which is pretty common. I think this might have been popularized by Daniel Pohl from Intel, but I think it was possibly in use earlier. Anyway, you render a mesh and then use piecewise linear approximations to the exponential function of the lens. And it looks just as good. You really couldn't tell the difference, even if you knew which one you were looking at in most cases. And that also allows us to benefit from the high-quality texture filtering of the GPU, which is also much faster than trying to do something on a per pixel basis. And it also allows us to do the latency correction I mentioned simply by shifting UV coordinates that we're reading from for the mesh. And we can also read from different UV coordinates for the red, green, and blue channels, because remember that a lens does aberrate the red, green, and blue subpixels differently. So as you can see in the bottom left, the panel is showing the health and safety warning with a slightly different location for each channel. After they go through the lens, they should line up by the time they hit your eye. But as some people have already alluded to at this conference, tuning the distortion parameters is a bit more of an art than a science, and the way we've designed our distortion mesh and lens and head-mounted display is all kind of such that you get the least overall aberration for the distribution of eye poses that you may have across the population who's using it. So it's not perfect. There are cases where it will still aberrate, but we try to minimize the overall aberration for everyone. Okay, so time warp is the technique that I mentioned about latency correction. The way it works is by offsetting the UV coordinates opposite your head motion. So if I'm looking this way when the frame starts to render, and I'm looking this way by the time the frame stops rendering, then we can just shift the image opposite your head rotation. And that way, all the optical features in the image line up with where they were at the last time you saw those features, so that you get lower perception of the world vibrating or like lurching as you move around. If you did not have time warp, then every time you started and stopped moving your head, or if you moved irregularly, the acceleration would cause the image to wobble. So the whole world would seem like it was shaking. And this is still an issue even with time warp if you translate your head. So most of the error in rotation in movement is due to rotation of your head. But you can contrive cases where you have like close-up content, you move your head side to side, and you can still see it kind of shake if all you're doing is time warp. So we also have a newer technique called space warp, which I'll get to later. Unfortunately, I can't talk too much about it, but it corrects for that positional error. So this is all kind of stuff we had in place by the time DK2 shipped. Who's used DK2? OK, a few more people. Yeah, so DK2 improved on the resolution. It moved to an OLED display, an LED instead of an LCD display. And it also had this time warp, but it was occurring once per frame. And unfortunately, apps don't always render at frame rate. It's really hard to do, as some of you may know. So we also added the ability to have time warp preempt your rendering. So if you drop a frame, we will come in and reproject the previous frame one more time, and that'll correct some of the error. And it's important to do this because of some perceptual factors around. Shoot, broke my segue here. OK. Optical flow. So if you're not moving the world to counteract head motion, then as I mentioned, it starts to feel like it's coming with you. And your brain knows that your head is moving, even if it doesn't see the world responding, because you have another sense inside your ear. You have a fluid-filled sac with a hair in it, and you can detect pressure changes based on acceleration, even if you close your eyes. And so your brain's constantly comparing the signal that it gets from that to the signal it gets from optical flow. If they don't agree, you start to feel nauseous. So who here has felt VR sim sickness? OK. Yeah, it's pretty similar to car sickness. So that's often caused by the same thing. You're looking at like a page close to your face, and that's not moving, and the car's moving. Your brain says, hey, something's wrong. I don't want to guess why, but some people think it might be because primordially we like ate something unhealthy, and that caused brain dysfunction. Anyway, just those stories are not that interesting. OK, so another pair of cues that your brain is always comparing are accommodation and vergence. And I just want to give this as kind of a canonical example of systems your brain is comparing. Accommodation is focus distance. So when you move something close to one eye, you have to focus at different distances to make it sharp. And so the background to the foreground will get blurry as you accommodate one range. Vergence is the only thing we control on the headset. So there are places where you can put content in the app where it will either make you feel cross-eyed or make it look blurry. But fortunately, we've put the what we call the zero parallax plane, or the bowl shape after it goes through the lenses, far enough away from your eyes that there's no distance too far. You're only going to feel discomfort if stuff comes too close to you. And it's somewhat related to the speed of movement and the range of depths that you're seeing. So if you're quickly jumping between something very far away and something very close up, that's the most likely to cause discomfort. So if you have like the user, I don't know, grabbing something and pulling it up to their face, and you also have like mountains in the background, and for some reason you have them looking quickly between those two things, likely to cause a sensation of blurriness. And there's an excellent paper by Marty Banks' lab, Shibata, characterizing the range of depths that will cause discomfort. In general, Banks' lab has put out a lot of excellent publications along these lines. And another thing that your eyes are also always doing is comparing the two images. The vergence is just one of the ways that your eyes compare the images that they're taking in. Optical features that are not physically valid will cause like very noticeable sparkling in the image. So if you have aliasing that's not consistent between the two eyes, like the lower resolution the eye buffers are, and if you don't use the right kind of filtering, or if you use techniques like FXAA or SMAA, image space anti-aliasing, in some cases, not all, and don't take this as like written in stone, but there are cases where physically incorrect or things that don't statistically converge to the right values will cause sparkling and discomfort. So we can't get away with all the same old tricks that we used to use with deferred renderers. yeah, we already talked about this, but yeah, there's the vestibular sense and the optical flow. Another thing that this affects is the field of view. It's very important not to use just any field of view. You have to use one that corresponds to the headset or the range of the headset's visibility that you're exposing. So if you do want to reduce the FOV, it's a good idea to also reduce the area in the render target that you're rendering to. If you were to only reduce the FOV, then things would move too quickly, and again, you'd feel sick. Another thing that causes inconsistent optical flow is if we don't do any latency correction and you're dropping frames, then that world wobbling with you. So this is just kind of tying it together. The image error grows pretty quickly as soon as you drop one frame. So how can you avoid dropping one frame? Well, there's a lot you can do. One of the things people typically get bottlenecked on after converting an app to VR is fill rate or texture bandwidth. So if you have a 1080p app that was used to rendering at 30 hertz and suddenly you're rendering at 90 hertz and you have probably 6 times more pixels per second being rendered, chances are that your whole engine or your whole app was kind of tuned for a workload that's now spending a lot more. It's rendering a lot more pixels than it was before, and so you need to figure out ways to cut down on the number of texture lookups you do and the number of pixels you're shading. One thing that can help a lot is memoizing distant geometry or trying to bake as much of your shading as possible. So try not to do specular effects if you don't need to, or have like cheaper fallbacks. Unity has a great fallback system in its shaders, so you can use complex shaders for stuff that has a lot of perceptual salience and save the GPU on stuff that's not. Definitely always use bitmaps, trilinear filtering, and isotropic filtering. You'd be surprised how many apps don't even generate bitmaps, and then it's just doing tons of aliasing and sampling from MIP level 0, which is a huge waste of bandwidth. So you can run. We actually have a tool now, OVRLint, in our utilities. So in addition to Unity's built-in VR offering, Oculus has a package you can download with some helper scripts and prefabs. And one of them is OVRLint, and it'll audit your project for setting issues like that. So if you're not generating bitmaps, not using trilinear filtering, if you have like way too many draw calls, and we'll get into the recommended ranges later, you can run this tool and it'll hopefully point them out for you and help you correct them. However, some corners aren't a good idea to cut. You don't want to have physically incorrect reflections. Each eye should see a different perspective of the reflection. So it is a common temptation for people to render one perspective of a reflection and try to reuse it for both eyes. And that usually looks wrong unless it's not a very salient feature. Again, you can get away with quite a bit if what you're doing isn't that noticeable. So take all of this with a grain of salt. What do they say? If it's good computer graphics, it looks good, and if it looks like computer graphics, it's bad. Horrible misquote, by the way. Targeting multiple platforms. So I'm talking about the Rift and Gear VR here. However, regardless of your headset, this is probably within the right order of magnitude. However, I will once again plug our ASW technology does allow you to render at half the frame rate that you normally would for other PC headsets. And still get the same responsiveness. So ASW, asynchronous space warp, which is really nothing but a pun on asynchronous time warp, allows you to reuse previous image data to compute intermediate frames for 90 hertz rendering with some small artifacts. So here's an example of kind of the visual outcome. We do not have this on Gear VR, but we don't need it because you don't have positional tracking. So you can actually just render every other frame at 30 hertz, and in most cases it looks pretty good. Animations will judder, but that's not going to cause your user to feel nauseous. So this was kind of motivated by position tracking on Rift. But on Gear VR, we kind of tried to set people's expectations about fidelity. And the default eye buffer resolution is only 1024, so the pixel workload isn't all that much worse than a typical app on Android. On Rift, we went the other way and we made it panel limited. So at the center of the screen, you have one texel in the eye buffer per pixel on the display, and it only goes higher from there. So as you go to the periphery, you have up to 2 pixels per texel. Vice versa. So even though we're cutting a lot of corners on Gear VR, you're going to be bottlenecked on almost every resource there. Typically, first people are CPU bound because of the tiled renderer. a lot of the work you do will get replicated across all the tiles. So if you have primitives covering a lot of tiles, you might want to optimize that a bit. Try to do as much batching as possible. Try to cut down unnecessary draw calls as much as you can, and reduce the mesh complexity. But then once you've fixed all of that, you're probably going to be bandwidth limited anyway on GearVR, just because it's a phone. So you typically have about 10x less resources per second on GearVR than you do on Rift. And beyond that, even if you're hitting frame rate on GearVR, you can quickly drain the battery and cause overheats as well. So it pays to continue optimizing until you can run, depends on how Spartan you want to be, but you could get down to the CPU level 0 and GPU level 0 and run for 3 hours if you want the app to run that long. We took that bet on Netflix, and it turned out to be a pretty popular app. So if you want your users to not have overheats, we do find those overheats correlate with people exiting apps, of course. Our SDK will also recommend particular values. You don't have to use them, but they're kind of where we found the optimal trade-off between quality and performance. So on most Adreno GPUs, it's 2x MSAA and 2x NISO. Actually, on some Mali GPUs, 4x you can get away with. We call these free, but it's kind of like marginal. The ROI is pretty high on them. Use ASTC compression and try to minimize the amount of texture data you're working with. Baking atlases and trying to optimize the locality of your texture accesses will help a lot. And once again, MIP mapping. You'd be surprised at how many people don't do this. And some of that also applies on Rift. But typically, there's just a lot more gross waste of shading and texture bandwidth on Rift, and you can kind of just look at it in the GPU profiler and quickly cut out the waste, which we'll get into in a moment. If you're shipping to our store, you generally want to not rely on asynchronous space warp to make frame rate on our recommended spec machine. We've set a baseline kind of machine configuration, which is an NVIDIA 970 or an AMD R9 which are similar performance. Actually, the R9 is probably a little bit lower, so you might want to target that. And then the CPU tends not to be as much of a bottleneck on Rift. If you can hit frame rate with that rec spec machine consistently, then you can also run with ASW on much lower spec machines. So our rec spec is kind of what we recommended at the time Rift launched, and our min spec is something we published with the advent of ASW, which is around the time Touch launched. And that really widens your potential audience. So if you're able to hit 90 hertz on rec spec, you're going to really be able to broaden your reach across all the hardware we support. So how do you cut down on shading rate? Well, one of the first and most obvious things is the iBuffer resolution. As I mentioned on Rift, we default to a panel limited case. And you can easily dial that down and not get a huge visual degradation. So I find that going as low as 0.7 sometimes isn't even noticeable, depending on your content. If there's a lot of high frequency content, then you're probably going to want to keep it high so you can see all of that. But we do have an overlay system, so if you only want to render some of your content with high spatial frequency, like a video, you can do that. You can render it to a quad or a 360 video can be rendered to a cube map. And then we raycast into that and directly sample it, bypassing distortion. And so not only do you preserve the full detail of the original image, you can also get panel limited visuals, which on GearVR is usually pretty prohibitive. The API for changing that render scale is in VR settings, so it's unityengine.vr.vr settings. There's also a new viewport render scale, which you can change dynamically. So if you don't want to permanently change your render scale, you can actually adjust it every frame. And it'll just stay at the largest allocated size. There's a little bit of overhead, so it's a little bit more expensive than just dropping the render scale permanently. But that allows you to quickly throttle. And we do offer adaptive pixel density. So you can just check that box and set the upper and lower bounds. We will allocate to the upper bound and then scale the viewport in when we detect that you're approaching when you exceed 85% GPU utilization. then we will automatically drop the resolution bounded by the lower bound you set. And once it hits the lower bound, then we just start dropping frames and using ASW. It's also worth noting that if you are in a phase where you're exceeding 85% GPU and you're already dropping frames, ASW will kick in and there will be very minimal hitching, and we will wait until your GPU utilization goes down before turning ASW off. So if you are CPU bound, ASW will stay on. So you may think that we're locking you into ASW and it's somehow related to adaptive resolution. We can tell whether you're CPU or GPU bound, and if you're CPU bound and we have ASW on, we may not scale down the GPU utilization at all because we know that it wouldn't help. You can also have the left and right eye buffers mapped to the same texture if you want to render monoscopic content and save bandwidth. And it's worth noting, not that this is really a performance-sensitive thing, but you can render whatever you want to the main monitor. A lot of people don't notice this. So you can set the output monitor of the camera, and it will be obviously more expensive if you render a totally separate view. Right now, what we do is a pretty cheap blit from the left eye buffer, and then we do a pan and scan to make it match the window. But if you want to render something else, you can. Okay, so now onto what we were promising from the beginning, which is workflow for debugging performance. So it's really hard to hit frame rate, especially on Gear VR. So this is kind of a general cookbook for how you can understand your app's performance and triage issues, and then go in depth on a couple of the ones that we commonly see. So as a workflow, we have some high-level tools, OVRMonitor for Gear VR, and the perf HUD for Rift. And there's actually a perf HUD in development for Gear VR that should be available shortly. You enable these, and they'll tell you how many frames per second you're dropping, what the current latency is, how much time our compositor is spending each frame. And you can kind of rule out large classes of possible issues. This can be important because it's really easy to end up chasing red herrings if you don't. So if you find that it's dropping frames and your CPU profile shows like a huge bubble somewhere, I wouldn't even look at the GPU performance unless the CPU bubble is that it's waiting for the GPU, which should be a smoking gun. And then you can kind of dig in with the tools that I'll talk about in a few minutes here, typically Systrace and Unity's Profiler. Or on Windows, you can use Windows Performance Analyzer if Unity's Profiler doesn't capture the information you're looking for. And then if it's GPU bound, on Rift, it's a lot easier. Unity does have a working GPU profiler for PC. Unfortunately, graphics drivers don't implement the queries that are needed to provide that information on mobile, so there are other tools available, and we'll get into those shortly. So supposing you're CPU bound, Unity has a hierarchical view in its profiler, which I have a screenshot of here somewhere. Okay. In this case, it's GPU bound, unfortunately. And I think that Oculus wait for GPU scope was renamed, so it's now like VR device.gpu or something. But in a more CPU-bound case, you would see stalls around like physics processing or like draw call submission. That even if it's CPU-bound, it can still have a stack in the draw call generation. In which case, you probably want to look at like using more batching. Here's what our performance HUD looks like on Rift. You can bring this up using the Oculus debug tool, or there's actually a hotkey, which I forget, so use the debug tool. And this has been expanded since this screenshot was taken, so it will now tell you how many compositor frames are being dropped, how much time the app is taking to render, how much time the compositor is taking. Typically, the compositor is more our problem. If you find that's a bottleneck, just report a bug. But yeah, you should be able to quickly rule out whether you're CPU or GPU bound this way. In general, you might find there are inefficiencies in your app that don't matter. Try to focus on the most important thing first. It's easy to prematurely optimize. And you'd be surprised what the system's doing. You may think it's bottlenecked on texture bandwidth, but then it might turn out to be something totally different. So it's always better to actually observe what it's doing. I generally try to change one thing at once unless I really know what I'm doing. If you change 3 things at once, you're in a totally new configuration, and it may be hard to understand the differences. These are things that commonly bite people when they're debugging performance issues. Sorry, I think we covered everything. OK, so on GearVR, as I mentioned, you typically can't afford to submit more than 100 draw calls per frame, which is extremely low. Unfortunately, that's just kind of how it is with tiled rendering and a 60 hertz refresh stereo. You can get away with more, and you can also get away with more vertices and triangles, but you're just going to have to probably find clever ways of making it all fit. And then we typically recommend single pass shaders, so you don't want to have like a lot of different shaders all being done in different passes. That's gonna really start to multiply the cost. And before you dig too much into the profile, it's good to kind of incrementally track your performance throughout development. If you find that like an artist just added, like a fully tessellated torus as like a shoelace hole in a boot, you might want to just bisect to that and remove it and not spend too much engineering time. It's good to have scripts auditing these things. It's not that hard to write an asset pipeline step that just checks how many triangles are in this mesh before adding it. Unity's profiler also has this excellent timeline view, so you can see exactly what the job queue was doing and what the sequence of operations was for the frame. So we've seen cases here where due to thread prioritization, physics was accumulating and spiking, and so you'd see no physics work getting scheduled for a long time, and then suddenly it's a spike. And that doesn't show up in the hierarchy view, except that you look at a few frames and it was 0, and then suddenly it's huge. But you can get a much better sense of kind of what's going on with this view. But unfortunately, it's mostly CPU focused, except that it will sometimes tell you that it's waiting for the GPU. Unity also has kind of always evolving logcat data you can get through the internal profiler. So if you enable this, it'll dump periodic reports of the amount of time rendering took and other important stats. This is kind of what it looks like. Again, getting kind of lower impact and higher benefit changes first, and trying to do easy, very telling things early, and then don't dig into GPUView until you know you need it. But here we are, GPUView. So one of the most powerful tools we have for performance analysis at Oculus, and we use this constantly, is ETW, Event Tracing for Windows. So when you run your app, you can insert instrumentation that gets dumped pretty efficiently and doesn't really affect the performance that much. And then you get this trace generated that you can then load up in a variety of tools in Windows. So the one you may be familiar with is Windows Performance Analyzer, which is a more detailed hierarchical view, sort of similar to the one I just showed you from Unity. There's another view available from the tool GPUView, which, how many of you have heard of GPUView before? Very few, and that's unfortunate because I'm sure everyone in this group could really benefit from it. This is like a super low level system hardware queue level view of the events retiring. So you can see what GPUView terms packets queuing up on each hardware resource. So you can here see on the bottom 2 CPU work getting submitted, and then fences getting submitted behind them. And then the CPU work spawns GPU work, and then you can see the GPU work causing faults and then waiting for them to resolve. And then we can say, oh, there's a vertex buffer that was too big. Wouldn't have seen that in Unity's profiler. Consider that a feature request. We do have some custom events that you can insert to help understand the trace when you get it back. IHVs have, actually they've been converging on more standardized events, but in the past they had kind of unique events that you'd be looking for the vsync operation associated with our swap chain. We render VR directly to the Rift display without going through Windows' usual compositing, and that's called direct mode. And so there used to be some nuances in the trace due to that, because typically what my workflow in GPUView is dump the ETW with the manifests installed, load it up in GPUView, and then find the vsyncs first, and then kind of zoom in on like a 10 frame or so interval where I think the problem's occurring, and then kind of compare to healthy frames and see how it's scheduling. So the vsyncs kind of become your navigation unit. So this is a little bit dated, actually. OVR log has been supplanted by a new tool called Oculus Monitor. And you can run that tool and enable and disable ETW logging. So typically you run Oculus Monitor, click Tools, Begin ETW Trace, then run your app, reproduce the issue, and then go back to the tool and click Tools, Stop ETW Trace. And then you'll have an ETL file that you can load up in GPUView. So here's what I was describing before, where in GPUView you can find your process. It's going to have all the processes in the system. You can filter it to the ones you're interested in, but it also helps you see inter-process contention. If you have two VR processes running, that's going to cause performance issues in some cases. So you can really get a lot of information in GPUView that other kind of more specialized tools don't give you. But the trade-off is that it's kind of information overload, and you have to really know what you're looking for. So the way that the packets appear in GPUView is that they stack up vertically for any given time. The height of the stack will shrink as work is finished. So for this time frame, you can see initially there was one packet, it immediately retired. Then we had two, and then there were some pink fences put in behind them. And then some more work was queued up behind those fences. So we're basically trying to guarantee that the purple work on the bottom retires before the purple work on the top. And then the purple work on the bottom spawns some GPU work. The bottom queue is the CPU. If I showed you the whole screenshot, which I did before, you'd be able to see that one of those gray areas is the CPU queue, and the top gray area is the GPU queue. And by clicking on the packets, you can see the dependencies between them. But then you can see that the fence kind of waits until everything else is drained and then disappears. Unfortunately, we don't have a tool quite as good as GPUView on Android yet. However, we do have Systrace, which will give you almost as comprehensive a view of what the CPU is doing. It is system-wide. It's pretty easy to use with ADB. You can dump, it's like a large HTML file. Sorry, this is OVRMonitor, which you'd use to triage before running Systrace. But like the perf HUD, it'll tell you whether you're CPU or GPU bound, and it'll also tell you the sequence of operations in your VR API call. So VR API is our mobile SDK, and on PC it's libovr. They're technically separate SDKs, but when you abstract them with Unity, they work the same. And it'll also tell you the current CPU level and clock frequencies. And it'll give you a preview each frame. So you can see in the top right there just the final iBuffer content. So you can kind of see latency in the delays between calls. And you can infer that graphics work is what was blocking because iRendering was long there. So you see that took 8.46 milliseconds to render the iBuffers. And so then I would conclude that it's GPU bound and dig into the shading and texture resolutions. But if it's CPU bound, as I mentioned, Systrace is a really powerful tool. Like GPUView, it's really low level, and it's going to potentially give you information overload. So try to reproduce the behavior while it's dumping, and then zoom in. It's got a nice UI in your browser, and you can quickly kind of zero in on problem areas. And it'll also show you contention between processes. If you want GPU data like this, unfortunately, there isn't, as far as I know, a cross-vendor solution. But you can use, actually, NVIDIA Tegra tools work pretty well in a lot of cases. But I recommend Mali Graphics Debugger if you're on an ARM core, and if you're on Qualcomm Snapdragon Profiler. These are continually evolving, and right now, they provide about it. They provide performance counters, and they'll tell you if expensive operations are occurring, like on resolves and copies to sysmem. So there's also API trace, which works a little bit like GL intercept, but will give you kind of a replayable trace, and it's especially useful on PC if you want to like kind of isolate the graphics work and not have to rerun the app repeatedly. Well, I guess we're way ahead of schedule. Any questions? We have 5 minutes.
Beautiful, man. That was outstanding talk, man. It was
Thank you.
From the high level to the low level. I mean, I used to see like there was an old Palmer Luckey talk that basically covered what is VR and how to best use it. Oh, beautiful. So I have really two questions. First one is for the optimization. What tricks have you found? Like there's using like blob shadows, maybe even offsetting the gravity and doing it through your own math in terms of Unity. What other kind of tricks have you found that work, especially for the Gear VR, that where it's
So for shadow rendering, yeah, blob shadows, cheaper projector shadows are going to save you some extra bandwidth. When you're rendering to the cascaded shadow map, that can cost quite a bit of bandwidth. Really look at the resolution and the number of cascades you're using. And then try not to use like expensive filtering. But it pretty quickly hits a pretty low quality level. So I do use projector shadows in a number of cases. In general, on Gear VR, you're going to want to bake as much shading as possible and kind of use clever tricks all over the place. So I don't know if our Rocket Toss app is still available, but we actually baked all the specular reflections in that. And there's a number of Gear VR apps where like it looks specular, but it's actually not, and we're just relying on the fact that your head can't move.
Super nice. Yeah, well, these kind of tricks. And the other question is, I guess what Google announced this the idea of a VR standalone VR whatever mobile device essentially.
Right.
And now that you're not limited by having it fit in your pocket. And you could have battery space and space for processors. And what is your dream? Like, what is your dream if you had unlimited, resources? What would you?
I personally, yeah, I'm a huge fan of standalone VR. I think that does afford a lot of nice options. As you know, at our OC3 event, we were demoing the Santa Cruz prototype. And yeah, we were able to clock it pretty high and get pretty good ventilation in there and do positional tracking on that device. There's a lot of really cool opportunities. And I think the untethered aspect is really attractive as well.
You're at the forefront. Thank you for that.
Thank you. Mm-hmm. Any other questions?
Hi, great talk. Thank you.
Thank you.
We ran into a project with one of our, or a problem with one of our projects where we had a video running at a fairly high bit rate and everything was fine. But then the update that introduced asynchronous space warp, it introduced a lot of judder because space warp would, or time warp and space warp, or whatever combination of the two, would kick in and cause like a desync of the audio and the video.
Oh wow. Okay.
This was in Unity, but I guess the question is there any way around that other than just lowering the bit rate of the video? Are there any interesting tricks that you know of to optimize video playback?
Good question. So that, I believe, was a bug with the interplay between rendering frame rate and fixed update. I kind of remember that bug. But in general, Unity does allow you to schedule work that is not dependent on the graphics frame rate and in the fixed update. And you can control the rate of fixed updates in the fixed update size in, I think, time settings. Yeah. Unfortunately, though, that doesn't mean that they're going to be distributed evenly in time. So when they get run is before update. It just has a state machine where it just figures out how much time is accumulated since the last time it purged, and then just like runs through all the fixed updates it needs to get back to 0, and then continues with the update. So if you're doing like video decoding or something that does take the whole fixed update, that can be problematic. So it's more about like picking the right buffer sizes, and unfortunately, being the real-time deadlines in VR are just a little bit firmer than they are in regular rendering. You might just have to figure out ways of staging the decode or making it more asynchronous and having more buffering. By the way, I should plug now that OVRMonitor has a setting where you can have all of our pose updates occur in the fixed update. So if you're doing something that is very physics intensive and you want to have like kind of lockstep execution with the physics engine, check that box. And if you're more concerned about like having it register perfectly with the visual, then don't check it. If you there are trade-offs. Unfortunately, there's not like a one-size-fits-all solution. It's either gonna be kind of one lockstep with physics or lockstep with rendering. And it sounds like the same kind of problem is occurring with your video decode. Any other questions? Sure.
The last question, I believe it was Oculus Connect 1. I had cornered John Carmack in a hallway somewhere, and he mentioned that on the Gear VR, he thought it was very important to do a special pass on all UI elements, kind of you basically set them on their separate render layer. I've since looked in the documentation, maybe I didn't look hard enough, but I can't quite pin down exactly how to do that. And on our Gear VR apps, we run into a lot of aliasing issues in the UI element. So I was wondering if you knew.
Yeah, that's actually, unfortunately, that was not easy to do at the time of OC1 because we had just implemented the overlay system. But now Unity does expose the OVR overlay utility. I'm sorry, we expose that through our utilities. So you have to download the Oculus Utilities package, import it, and then you can take any quad primitive, add this script to it. It'll use the same reference frames and everything, but it'll render it with that ray casting that I mentioned. It will not appear in the preview on the main monitor, but if you're on Gear VR, it should make no difference. It'll just look sharper. You can also have it depth sort properly. We'll poke a hole in the alpha channel, and background content will show through for bandwidth cost. But the render texture that you assign to that can contain the output of View GUI content of View GUI, so you can still have regular UI showing up that way. You can also have it render as a cylinder, which is kind of how our home app is rendered.
Awesome, thank you. Mm-hmm. That's great.
I think there's another one over here. No? Okay. Okay, well, thank you for your time.